electron configuration and also learn about how to draw orbital diagrams in this video. So let's begin. This is a periodic table without having actually elements in that, and there is a reason. We want to know how a periodic table is divided into different blocks. So first of all, we have periodic table divided into different parts, and these are two kind of pillars which are sticking up. I call these as pillars. The one on the left side we call as S block elements. The one on the right side we call them as P block elements. Then we have some elements which are a little bit sinking. We call them as D block elements. And then we are having some elements here which are sinking deep down, which we call as F block elements. Actually, each of the row or period for periodic table that corresponds to principal quantum number which we learned in earlier video, which is just n equal to 1 and so on. When we are in S block, we will use the letter S. When we are in P block, we'll use the letter P, and so on. There are some more rules, of course. As we go on moving across from left to right, we add extra electron. And also for S and P, we are going to keep the same number for N. But for D and F is going to be different. So let's begin. The first one which we have here, this one says 1s1. What this stands for is 1 is the principal quantum number, S is the sublevel, and that has 1 electron. The element which we get here is hydrogen. So in fact 1s1 is the electron configuration for hydrogen. The element which comes here is helium. And helium has 2 as the atomic number. This is the only exception which we have when there is an S subshell in the P block. So helium belongs to S orbital, and the structure which we get is 1s2. So what it indicates is there are 2 electrons, its main principal quantum number 1, and there is S sublevel. In that there are 2 electrons, and that's all we have for helium. So as we go reading, it will be 2s1, this will be 2s2. When we go across in second row, it's 2p1, and you can easily fill in the gaps. It's 2p2, p3, 2p4, 2p5, and so on. So very easily you can complete each of those, or without even completing all. If I just want to find out what I need to have, this is 17 as the atomic number, and I can look at the row number 3 and I can count. It's 1, 2, 3, 4, 5, and I can write down as 3p5. Or maybe if I'm in S here and this is row number 5th, 5s1, the next one should be 5s2. If it is row number 7, this should be 7s2. So that takes care of S and P sublevels. When we go to D sublevels, we go one level lower. So we go to n-1 level. What it means is, if I'm in row 4, this will be 4s1, this will be 4s2. But when I come here, this is going to be one level below. So I'm going to go to 3d1, 3d2, 3d3, and so on. So if I'm looking at, say, this number here, number 44, it's row number 5th, but actually it belongs to D, so I'm going to go 5 minus 1, which is 4, and then I can count how many electrons I will have. It's 1, 2, 3, 4, 5, and 6, so it will be 4p6. Now what happens with F orbital? With F orbitals, we go to n-2, we go 2 levels lower. And this actually, the first row which we call lanthanides, is extension from level 6, and the actinides is the extension from 7. So whenever we are going to use F orbital, we are going to use minus 2, going 2 levels below. So coming from 6th level, this will be actually 6 minus 2, which will be 4. So we'll have 4f1, 4f2, and so on. And when we come to the next one, this is actually 7th level, but we are going to have it 7 minus 2, which will be 5f1, 5f2, and so on till 5f14. Now I want to tell you one simple thing. Keep in mind, S orbital can only take 2 electrons. We only got 2 elements in S block. P has 3 orbitals, and each orbital can take 2, so we get 6 electrons. And look how many elements which we got here. We got 6 elements. D has 10 and F has 14. Now ideally we can write electron configuration beginning with 1s1, 1s2, and we keep on writing. It's just practically not possible to write every single orbital. So what we do is we select the element and we actually write down the last subshell which is completely filled. And let's talk in more detail with the next one which we have here. So that's the periodic table, and in this there are elements and there's atomic number given. You need to spot the element and find out the atomic number. Now the problem which you're going to work on, we're going to work on cobalt, which actually I highlighted here, which is right here in row number 4th. And then this is belonging to d orbital. So when I have to write down cobalt configuration, I need to get cobalt with the atomic number 27, and I'm going to start reading from left to right until I come to the point when I reach cobalt over there. So let's see how it is done. Okay. So we're going to write down for cobalt the electron configuration, and as we know, cobalt is 27, and that's where we need to reach. That's your level 1. Now remember the rule which we learned about. Every lower energy level must be completely filled in before we move on. Since cobalt is in energy level 4th, that means all the energy levels which are before this must be completely filled, which makes it actually very simple. So level 1 is completely filled. What do we have? It's 1s1 and 1s2. We simply write the ending one 1s2. Then we go to level 2. Level 2 has these two, which are s electrons. That's completely filled. So it's 2s2. This is 2p. Remember, we are in the p block. That's completely filled in. So we are going to write 2p6, because we know there are 6 elements and there will be 6 electrons there. Then we move on to row number 3. Again, that is completely filled in. So that is this will be 3s2 first. The level 3s is filled in. Then we get to 3p6, and now we come to 4th level. In 4th level, these are s. So 4s2 is completely filled. And now when we come to scandium here, that is d sublevel. Remember what we say? In d sublevel, we have to step down, we have to come to 1 level lower. So even though it is 4th period, 4th row, it is not 4d, it is 3d. So it's 3d orbital, and cobalt is right over here. So let's count how far is cobalt. It's 1, 2, 3, 4, 5, 6, and 7. So we got 3d7 as the ending configuration for cobalt. So what we got, all of this is electron configuration for a cobalt atom. That wasn't that difficult, right? Now let's take this to 1 level higher. We are going to go to the orbital diagram using our electron configuration. Remember, S only has 1 orbital, P has 3, D has 5, and F has 7. And we are going to show that by simple small lines there. So that's going to be my 1s. one line. Next comes 2s. 2s is going to be one line. Then I get 2p, and 2p is going to be 3 lines. What comes after 2p is 3s. 3s will be again one simple line. Then we get 3p. We get 3 lines for 3p. Then we get 4s, again it's one line, and when we have 3d, which is 5 spaces, so we put there 5 spaces. And then how do you fill in the electrons? Remember the rule, every orbital must be completely filled in. So I am putting 2 electrons into every possible orbital which I have before that last sub-level, which is 3D. Now look carefully. We are putting electrons with one arrow upward and one arrow downward. That's to indicate that we have 2 electrons having opposite spin. Now when we come to D, look how many electrons we got there. We have 7 electrons. And what do we know about the rule? The Hund's rule says that we need to have 1 electron in each orbital before we start pairing. So there goes 3rd, there goes 4th, there goes 5th. And out of 7, there are still 2 remaining. We start pairing them afterwards. So this is a real schematic representation of an orbital diagram for cobalt. So let's see if you understood that, and we can work on the next one, right? This is actually the same thing which you're going to do, so I'm going to skip this. Okay, there are some more questions about cobalt electron configuration. This is what we ended up getting, cobalt configuration. Let's begin again here. There are some more questions here. No, cancel. So this is what we got as electron configuration for cobalt. The question is, what are the highest energy level electrons? Those are the electrons which are the ending electrons. So 3d7 will be the highest energy electrons. The next question is, which are the outermost or valence electron? For that, you have to be careful. You need to find out the principal quantum number for each of the suborbital, sub-level which we have there. We have 4s2 and 3d1. 3d7 could be highest energy level, but that is not the outermost because 3 is smaller than 4. So 4 is the highest one, or we can call that as the outermost one, and therefore 4s2 will be the valence electron. I look at that as a simple way is, if you take the elevator to the 3rd floor, you can go to SPD all the rooms, and if you have to go to 4s2, you need to go to the 4th floor by the elevator. So kind of it tells you this is the outermost level which we have there. Okay. Now how many valence electrons we have? Those are the electrons which you found. So those electrons are 2. That means the valency for cobalt is going to be 2, or valence electrons are 2. So let's move on to the next problem. Alright, so in this question here, we are going to talk about sulfur. Okay, again. Okay, here is a question in which we are going to write down the sulfur configuration. No, cancel, begin here. This is a question in which we are going to write electron configuration and orbital diagram for sulfur, and sulfur is right over here. So if you look carefully, sulfur has the atomic number of 60, and we need to show how those electrons are arranged in an atom of sulfur. We are going to again read from left to right till we reach sulfur. So level 1 completely filled in, That's 1s2. Level 2, S is completely filled in, P is completely filled in, so it's 2s2 and then 2p6. Then we go to level 3, S is completely filled in, so 3s2. When we come to P, sulfur is right here, it's 1, 2, 3 and 4, which indicates we have 4 electrons in sulfur. So we got it as 3p4. How do we get the diagram, the orbital diagram for that? 1s will be one line, 2s will be again one line, then comes 2p, that will be 3 lines. 3s again is going to be one line, and then we get 3p, which will be 3 lines, 3 suborbitals. Electrons must be paired and all the sublevels must be completely filled in. So I'm going to get it done till 3s2. And then I look up at 3p4. We have 4 electrons and we have 3 orbitals. 1 electron goes into each of the orbital, and then the 4th, which is remaining, will be paired like this. So this is what we got for sulfur as our configuration. Which are the highest energy electron? You remember by this time, the one which we are ending with will be always the highest energy electron. But look at carefully, we also have 3s2. So on level 3, we have 3s2 and 3p4 as both in the highest energy level. So we can actually write down that 3s2 and 3p4 both are highest energy electrons. Out of them, of course, 3p4 are still at a higher level. Then we get the outermost electrons or valence electron. In this case, the coefficient which corresponds to the principal quantum number is 1, 2 and 3. Number 3 is the highest one, and that's why outermost will belong to all with 3. So it's 3s2 and 3p4 will be the valence electron. Well, how many are those? There are 2 from s and there are 4 from p orbital. So they will be 2 plus 4 as 6 electrons. Now this is interesting. Remember, every electron will try to become a noble gas. So if sulfur wants to become a noble gas, what it needs to do is simply it needs to get 2 more electrons. So if sulfur has 16, there is argon which has 18 electrons. It's very easy for sulfur to gain 2 electrons. So sulfur gains 2 electrons. So now what happens when sulfur gains 2 electrons? It ends up having a negative charge, and that turns into S minus 2. Remember, every atom strives to become a noble gas. Who doesn't like a royal life, right? We all want to have a royal life. So simply if sulfur can gain 2 electrons, it's going to become royal like argon. Now what will be the new electron configuration for sulfur ion? Sulfur ion has a charge of negative 2. The atom has 16 electrons, but now the ion has already gained 2 more electrons, so electrons are 18 for sulfur now. So how do you get the configuration? Okay, 1s2, 2s2, then we get 2p6, 3s2, and sulfur atom was 3p4, but now with extra 2 electrons, that's going to go in p orbital, and we are going to get 3p6. So this is almost identical to argon, but it is not argon. It will be isoelectronic. What we call is isoelectronic, having the electron structure similar to a noble gas. This is an interesting question. Would the resulting ion be larger or smaller than the original atom? Let's see sulfur atom. It will have electrons and protons, both 16 and 16, because there is no charge. If it is sulfur with negative charge, electrons and protons will not be equal now. Protons will still be 16, electrons are 18. Okay, protons have positive charge, electrons have negative charge. So protons attract the electrons and keep them in place. Number of protons here is equal, so there is a good control of protons over electrons. When we look at this ion here, the control over electrons is less because we have less protons than electrons. What it does effectively is it increases the size, so the ion becomes bigger. Ion which are negative, which will have larger size than the atom. Okay, this was the question which we already covered. Which noble gas does the sulfur ion is isoelectronic with? That is similar to argon. Argon has 18 as the electrons, and sulfur also has 18 electrons when it is a sulfur ion. Okay. So here's a question for you guys, and I hope you all can work on strontium. So I hope you can get the answer for this, and I will see you in next video.